Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The relentless quest to understand the behavior of matter at the atomic level has long presented a formidable challenge to physicists and chemists alike. The problem, at its core, resides in the complex interplay of electrons within a system of interacting particles, governed by the laws of quantum mechanics. The Schrödinger equation, the fundamental equation describing the evolution of a quantum system, in principle provides a complete solution. However, for systems comprising more than a few interacting electrons, solving the man-body Schrödinger equation directly becomes computationally intractable. This intractability stimulated the development of approximate methods, each grappling with the daunting task of balancing accuracy and computational feasibility. Prior to 1963, several approaches existed, each burdened with significant limitations. Hartree-Fock theory, a cornerstone of electronic structure calculations, offered a simplified picture by assuming that each electron moves independently in the average field of all other electrons. This approximation, while simplifying the calculations, neglects electron correlation, which accounts for the instantaneous interactions between electrons. This approach leads to significant errors in predicting various properties, such as the total energy of a system. Addressing these shortcomings became a central focus, driving the search for more accurate and computationally manageable methods. The year 1963 saw the publication of self-consistent equations including exchange and correlation effects by Walter Kohn and Jeu Sham, a pivotal work that fundamentally altered the landscape of electronic structure theory. The authors, recognizing the limitations of existing approaches, sought a new framework. Their work laid the foundations for what is now known as density functional theory, or DFD, a method that has since become a ubiquitous tool in physics, chemistry and materials science. The central premise of Kohn and Sham's work, and the underlying principle of DFD, rests on the Hohenberg-Kohn theorems, which they employed in the development. The first Hohenberg-Kohn theorem, a cornerstone of their approach, established a profound connection between the ground state properties of a system and its electron density. This theorem states that the external potential acting on a system of electrons is uniquely determined, to within a constant, by the ground state electron density. In other words, all the properties of the ground state, including the ground state energy, are functionals of the ground state electron density. This theorem implies that one can, in principle, determine all the properties of a system by focusing on the electron density, a function of only three spatial coordinates, regardless of the number of electrons. The second Hohenberg-Kohn theorem provides a variational principle for the ground state energy. It states that the ground state energy of a system is the minimum of an energy functional, where the functional depends on the electron density. The correct ground state density minimizes this functional, yielding the true ground state energy. This variational principle provides a means to find the ground state density. The implications of these theorems are far-reaching. They indicate that the complex man-body problem can be significantly simplified by focusing on the electron density rather than the full man-body wave function, which depends on the coordinates of all electrons. This dramatically reduces the computational complexity, a key intellectual precursor and an important consideration for the authors, with the Thomas Fermi model, an early attempt to describe the electronic structure of atoms. The Thomas Fermi model, though approximate, provided a simple connection between the electron density and the energy of a system, laying some groundwork for the development of DFD. However, the Thomas Fermi model suffered from several deficiencies, including its inability to accurately describe the electronic structure of molecules and its prediction of a divergent energy for atoms. The Kohn-Sham work directly addressed these shortcomings by incorporating the exchange and correlation effects that the Thomas Fermi model had neglected. The 1963 work by Kohn and Sham offered a new and improved approach to calculating the electronic structure of systems of interacting electrons. The methodology provided a rigorously justified, computationally efficient, and accurate framework for tackling the man-body problem. This approach circumvented the limitations of the Hartree-Fock method by explicitly accounting for electron correlation and exchange effects, and it addressed the deficiencies of the Thomas Fermi model by establishing a rigorous theoretical framework and a practical methodology that has profoundly shaped the field. The development of this approach, founded on the Hohenberg-Kohn theorems, provided the theoretical and practical basis for the widespread application of DFDE, transforming how scientists and engineers analyze, design, and predict the properties of matter. The focus of the next part will be on detailing the specific equations and applications within the Kohn-Sham approach, together with the evolution of this methodology. The Kohn-Sham approach, unveiled in 1963, presents a method for solving the man-body Schrödinger equation a persistent challenge in quantum mechanics. Its genesis arose from the limitations of earlier models, the Hartree-Fock method, while a significant advancement approximated electron interactions by treating each electron as moving in the average field of the others. This approach, while computationally manageable, neglected electron correlation, the tendency of electrons to avoid each other because of their mutual repulsion. Approximations such as the Thomas Fermi did offer simplifications, but lacked the accuracy to represent real-world systems. The Kohn-Sham approach deftly addressed both of these shortcomings. The cornerstone of the Kohn-Sham method, as detailed in the original paper, is the introduction of a fictitious system of non-interacting electrons. These electrons, unlike their interacting counterparts in the real system, experience an effective potential carefully constructed to mimic the complex interactions within the real system. The ingenious twist is that this fictitious system is designed to possess the same ground state electron density as the actual interacting system. This allows for the reduction of the complex mana-body problem to a simpler, more tractable one. The central component of the Kohn-Sham formalism is the exchange correlation potential. This term encapsulates all the mana-body effects arising from the complex interplay between electrons, encompassing both exchange and correlation. The exchange interaction arises from the antisymmetry requirement of the wave function, which dictates the electrons of same spin cannot occupy same space. Correlation, on the other hand, encapsulates the influence of the instantaneous positions of the electrons on each other beyond the average field approximation. Kohn and Sham recognized that the exact exchange correlation potential is known but complex. The equations which govern the Kohn-Sham system are the Kohn-Sham equations. These equations form a set of self-consistent equations. The equations are as follows. The first equation is the Kohn-Sham equation itself, -1/2 del squared acting on psi sub I of r plus the effective potential of r acting on psi sub I of r equals epsilon sub I psi sub I of r, where psi sub I of r represents the single particle wave functions of the Kohn-Sham equations, and epsilon sub I represents the single particle energies. The effective potential, as stated explicitly in the original paper, is the functional derivative of the total energy with respect to the electron density. The effective potential, V sub EFF of r, equals V sub x of r plus integral of the electron density of r prime divided by the absolute value of r minus r prime dr prime plus V sub x c of r, where V sub x of r represents external potential produced by the nuclei. V sub x c of r represents the exchange correlation potential. The total electron density then equals the summation from I equals 1 to n of the absolute value of the psi sub I of r squared. Solving the Kohn-Sham equations involves an iterative self-consistent field, or SEF, procedure. This involves initially guessing an electron density, constructing the effective potential, following by solving the Kohn-Sham equations to obtain a new set of single particle wave functions. These wave functions are then used to calculate a new electron density. The process repeats until the input and output electron densities converge. This process establishes the self-consistent solution. To make this method practical, Kohn and Sham provided a means to approximate the exchange correlation potential. They suggested the local density approximation, often abbreviated as LDA. In the LDA, the exchange correlation potential at a point is approximated by the value obtained from a homogeneous electron gas of the same density at that point. This approximation, while offering a tractable solution, did introduce inherent limitations. It assumes the electron density is slowly varying. The LDA, despite this limitation, provided reasonable results for properties like the ground state energies and equilibrium geometries of many systems. The impact of the Kohn-Sham approach was immediate and profound. It offered a framework which could calculate the electronic structure of atoms, molecules, and solids with far greater accuracy than prevailing methods. The approach's power stems from its ability to balance computational efficiency with predictive power. It was quickly adopted by the scientific community. The development of the Kohn-Sham equations directly benefited from the earlier work of Walter Kohn, along with Pierre Hohenberg. In 1964, Hohenberg and Kohn provided the theorems which established the theoretical foundation of density functional theory. These theorems demonstrated, for a system of interacting electrons and an external potential, the ground state energy and electron density uniquely define each other. This gave the framework of the Kohn-Sham equations a rigorous theoretical basis. The work of John Clark Slater on the exchange energy had significant influence. Slater's simplified approach provided insights into the exchange interaction and showed the potential of a density-based description. The impact of the Kohn-Sham work expanded rapidly. It led to the development of more sophisticated methods for calculating the exchange correlation potential. These included the generalized gradient approximation, or GGA, and hybrid functionals. These methods improved the accuracy of calculations by incorporating the electron density and its gradient, or by mixing in a portion of the exact exchange energy. Today, DFT is ubiquitous. Condensed matter physicists, chemists, and materials scientists routinely use DFT to calculate the electronic structure, properties, and behavior of materials. Its ability to predict material properties has revolutionized the design of new materials and chemical compounds. For example, DFT calculations are crucial in designing solar cells, understanding the catalytic properties of surfaces, and developing new pharmaceuticals. This enduring legacy of the 1963 paper lies in its elegant solution to the nanobody problem. Its impact arises from its combination of theoretical rigor, computational efficiency, and broad applicability, which continues to fuel scientific and technological advancements.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.